Hello everyone, welcome to this video. In this video, we shall see question from June 2017 consisting of 4.75 marks. The question says, which of the following polynomials are irreducible in Zx, the ring of integers, right? So these are the given four polynomials, right? So let us look at the first option. First polynomial is given to be x raised to power 4 plus 10x plus 5, which is of degree 4, right? So we can write the missing terms as 0 into x square and 0 into x cube, no problem with that. So now when you have a closer look at this polynomial, you'll find that there is a prime p such that all the conditions satisfying the Eisenstein's criteria, these are fulfilled, right? So you'll see 5 can divide 5 square, that is 25, do not divide the constant term, right? It doesn't p square does not divide the constant term, right? So it should be 5 over here, and but this p divides 5, it divides 10, it divides 0, it divides 0, but it does not divide the last term, that is an. So we saw according to this Eisenstein's criteria, this polynomial is irreducible over Q. But in the question, they are asking, is it over the ring of integers? So for that, we'll use another result, which is the Gauss lemma of irreducibility. It says that any polynomial is irreducible in Zx if and only if it is both irreducible in Qx, this we have obtained using Eisenstein's criteria, and it is primitive in Zx. And by primitive we mean the GCD of all the coefficients, it should be 1. So in the given polynomial, the GCD of all polynomials, this is equal to 1. They are relatively prime to each other, therefore both the conditions are satisfied. It implies that it is irreducible in Zx. Therefore option A is the correct option, right? So let us talk about the second option. Here we are given cubic polynomial x cube minus 2x plus 1, right? So how can we check this? One way for a polynomial with degree 3 is to check it using this result. In this result, it is reducible, any polynomial is reducible if and only if it has some 0 or root in that given field, right? Now we have to check whether we have any root for this polynomial in Z or not, right? So you clearly can see, if I substitute x is equal to 1 into this polynomial, I'll get 1 minus 2 plus 1, which is equal to 0, right? Therefore we have a root in integers, which is x is equal to 1. Therefore this is reducible in Z. But they are asking, is it irreducible? No, it is not. Therefore option B is incorrect, right? So now let us move on to the third option. The third option is biquadratic equation of degree 4, that is of degree 4, and we need to check its irreducibility in Zx, right? So as such we cannot find any root, or finding any root won't work over here. So for that, what we do, we use the mod p irreducibility test. This test says that if you have any polynomial and you can find a p, right, you can find such an p such that if you reduce this polynomial modulo p, that is you reduce all the coefficients modulo p, then you check the irreducibility of the reduced polynomial over Zp. If it is irreducible in the reduced polynomial, if it is irreducible in Zp, and their degrees are same, it implies that the original polynomial is irreducible over Q, right? So we need to find one p such that it is irreducible over the Zp, right? Integers mod p. So let us get started. Initially, let us take p is equal to 3. Let us see what happens. The original polynomial fx was x raised to power 4 plus x square plus 1. Now the reduced polynomial mod 3, that would be when you divide this 1 by 3, you'll get the remainder as 1. When you divide this 1 by 3 again, you'll get the remainder as 1, and again it is 1. Therefore, this is the reduced polynomial, right? And we need to check whether this is irreducible over Z3 or not. If it is irreducible over Z3, we would have found our P, and then we are done, and then we can say that the original polynomial is irreducible. If not, we'll have to look for another P, right? So to check its reducibility over Z3, what we do is we just see whether the elements of this Z3, whether they are root of this reduced polynomial or not. So we'll check it. F of 0, it is not a root. F of 1, it is a root, right? So x is equal to 1 is a root. So from here we conclude that f bar x, the reduced polynomial, is reducible over Z3. But now this polynomial is reducible, but we were looking for some P for which the reduced polynomial is irreducible, right? So this P won't work. We have to look for another P. Let us take P to be 2. So our reduced polynomial would again be this. That means fx was x raised to power 4 plus x square plus 1. When you divide 1 now by 2, you'll get the remainder as 1. When you divide 1 by 2, you'll get the remainder as 1. When you divide 1 by 2, you'll get the remainder as 1. So this is our reduced polynomial, and we need to check its reducibility over Z2. So what we do, we again go for looking for roots. The only possible roots would be 0 or 1, right? So we'll find f bar of 0 and f bar of 1. F bar of 0 is not equal to 0 mod 2, and f bar of 1 is again not equal to 0 mod 2. Therefore, we do not have any root over here. So from here, we cannot conclude f bar x is irreducible. Why? Because the degree of this polynomial is x is 4, right? And whenever degree is 2 or 3, and we in that case you got one root, then you'll say that that polynomial would be reducible. Otherwise, we cannot make conclusions about the reducibility of the polynomial whenever the degree is greater than 3, right? So we do not have any root. We are but we cannot say with surety that this polynomial is irreducible. The reduced polynomial is irreducible. So for that, we need to look for some factor of this polynomial. So this was our polynomial, right? So we'll go for looking for possible factors. For degree 2, the possible factors would be x square plus x plus 1. Why this is so? Because Z2 contains only two elements, 0 and 1. So the coefficients could either be 0 or they could be 1, right? So for degree 2, this should be 1, this should be 1. They cannot be 0 because otherwise the factor would be of degree less than 2, right? So now here I can have 1, 1. Otherwise I can have 0, 1. Otherwise I can have 0, 0. These are the only possibilities. Now for 0, 0, I'll be getting here it should be 1 only, right? Yes, for this I'll be getting x square. Now x square clearly doesn't divide this, so we do not take this factor, right? This factor is this one and this. So we'll go for checking whether this is a factor, whether this is a factor. So this can be done by using the long division process. So we can divide the given polynomial with the possible factor, and if the remainder comes out to be 0, that is a factor. So now in this case, this comes out to be a factor of the given polynomial, the reduced polynomial f of x bar. Therefore, this polynomial is reducible, right? So this polynomial comes out to be reducible. Therefore, option C is incorrect, right? For option D, we have again cubic polynomial. So let us look at our polynomial x cube plus x plus 1, and we need to check its irreducibility in the ring of integers. So again we'll go for this test. We have to find some p such that the reduced polynomial is irreducible. If that is so, if we found one such p, we'll conclude the original polynomial is also irreducible. So again, if I am taking p as 2, in this case, my reduced polynomial would be this. No problem with that. Again, I'm checking it over Z2, right? The only elements are 0 and 1. So I'll check f of 0 and f of 1. So now from here, f of 0 is not equal to 0 mod 2. That means 0 is not a root. This is not a root. F of 1, this is also not equal to 0 mod 2. Therefore, this is also not a root. In this case, I can conclude that this polynomial is irreducible in Z2 because the degree of this polynomial is 3. And according to this result over here, reducibility of a polynomial of degree 2 and 3, the given polynomial is reducible over f if and only if it has a 0. So we do not have a 0, therefore we say it is not reducible. So if the reduced polynomial is not reducible, therefore the original polynomial is also not reducible in Zx according to mod p irreducibility test, this test, right? So hence we conclude that the original polynomial is irreducible in Zx, right? Therefore option D is the correct option. Well, the only correct options are A and D. That is it for this video. Thank you for watching.